Class, you're welcome once again to another exciting video lesson. And in today's video lesson, we'll be looking at the hydrogenation of alkynes. Now, this particular video lesson is for students in college or universities that are in their first year. So it's an A-level video lesson, all right? Now, the hydrogenation of the alkynes is what we are looking at. Now, when you see the word hydrogenation in chemistry, the word hydrogenation, all right, is a type of reaction. Hydrogenation, it is a reaction that involves the addition of hydrogen to compounds. All right, so hydrogenation involves the addition of hydrogen to compounds. That is hydrogenation. So now we are talking about hydrogenation of alkynes. So that simply means we are adding what? Hydrogen to get what? Alkynes. Now, on a very good day, let me use that word, on a very good day, or on a normal hydrogenation process, all right? For a normal hydrogenation process, alkynes are converted to alkenes. Then alkenes, on continued hydrogenation, alkenes are further converted to what? Alkanes. All right. So these are it is. Alkynes under hydrogenation. All right. Under uncontrolled hydrogenation. That is hydrogenation that involves you using excess hydrogen. Uncontrolled hydrogenation. Alkynes are converted to alkenes and later to alkanes. All right. So it therefore means that under uncontrolled hydrogenation, alkynes are converted to the final product called what? Alkanes. Now, this is a common hydrogenation reaction we all know, even from A-level discussion. All right. Now, this particular reaction, the conversion of alkynes, all right, alkynes reacting with hydrogen to give us alkanes. Now, this reaction occurs in the presence of platinum catalyst. All right. So platinum is a catalyst that catalyzes the addition of hydrogen to alkyne, eventually converting it to what? Alkanes. So take for example, we have ethyne. Okay, so this is ethyne. So under uncontrolled hydrogenation in the presence of platinum, what are we going to get? We're going to get the alkane CH3. So ethyne was converted to what? Ethane. So now this is the general knowledge, but the core idea on this video, the core area we are going to focus on in this video lesson is on the controlled hydrogenation of alkynes. The controlled hydrogenation of alkynes. Controlled hydrogenation of alkynes. Remember, this is uncontrolled. So when you just use excess hydrogen to react with alkynes, they are converted to alkanes. So, all right. So it is not a controlled hydrogenation reaction. So it's just straight to get your final product. But then there is what is known as controlled hydrogenation of alkynes. Under the controlled hydrogenation of alkynes, there are two catalysts, all right, that are used. Now we are going to go into that area right now. So we are going to be discussing the controlled hydrogenation of alkyne. The controlled hydrogenation of alkyne. Now, under this controlled hydrogenation, the alkynes are converted to alkenes and not alkanes. Alkanes is the final product of the hydrogenation process when you use excess hydrogen. But now, when you use limited hydrogen, in order to control the products you want to get, the intermediate that we can get is the alkene. However, the alkene that is formed depends on the catalyst that is used. Are you with me? The alkene that is formed depends on the catalyst that is used. So the alkene you get when you carry out controlled hydrogenation of alkynes depends on the catalyst that is used. Now there are two main catalysts we can use for this controlled hydrogenation of alkenes. We can use the Lindlar's cat, what is called the Lindlar's catalyst, and then we can also use sodium in liquid ammonia. Okay, so we can use this catalyst and we can use this catalyst. Now what is the Lindlar's catalyst? Now the Lindlar's catalyst explains or the composition of the Lindlar's catalyst. Now the Lindlar's catalyst is not just a compound, however it's a mixture of compounds, right? Now there are two different compositions of Lindlar's catalyst, however both are generally accepted. Okay, so first we have barium sulfate with palladium poisoned with sulfur, or we can also have Lindlar's catalyst can also be palladium on calcium carbonate poisoned with quinoline. All right, so we can have this palladium on calcium carbonate poisoned with quinoline, or barium sulfate with palladium poisoned with sulfur. So these are the two compounds that can serve as the Lindlar's catalyst, the two mixture of compounds and elements, right, that can act as what the Lindlar's catalyst. Now however these two that you use, one thing is certain, you get the same product. All right, whether this or this, you get the same product. Now why is it very important to poison the compound? You see, if you observe, we have palladium poisoned with sulfur, and here we have poisoned with quinoline. Why is it important to poison it? So we are poisoning the palladium to be precise. Usually we are adding a substance to act as a poison. It is acting as a poison because it actually decreases something. If somebody is healthy and that person takes poison, the person's health begins to deteriorate, begins to decrease, begins to go down. So that was the main point of this. All right. The reason why we refer to sulfur here as the poison is because the sulfur tends to reduce something. All right, the palladium. And what does it reduce? The reactivity. All right, of the palladium. It reduces the reactivity or the activity of the palladium. All right. So that is why it is acting as a poison. Even for this quinoline also reduces what now? The activity or the reactivity of the palladium. All right. That is why we refer to it as what? Poison. So it is poisoning the palladium. So these poisons here are to decrease the activity or reactivity of what? Palladium. So now here comes the final secret that you need to know concerning this. Now please note that when Lindlar's catalyst is used, a cis alkane is formed, and when sodium in liquid ammonia is used, a trans alkene is formed. So when we use Lindlar's cat, what is the catalyst that is formed? Cis alkane. When we use sodium in liquid ammonia, what catalyst do we get? A trans alkene. All right. So now let me show you how we can represent this in terms of structure. So you can have this palladium present with sulfur, right, as Linda's cat, okay, Linda's catalyst. So when you have this, now this is what we are going to get. So we're going to have, remember, when we use Linda's catalyst, we're going to get a 6-alkene, right? Now, because there are 4 carbons, so we're going to have something like this now. C, 1 carbon, another carbon, and then another carbon. So this CH3, this is CH3 here. This CH3 is 1 here. And then you have, so one of these bonds was broken, that's hydrogen was used. So we have hydrogen. So this is 6 boots 2 in, alright, 6 boots 2 in, that's what we have, okay, 6 boots 2 in. So why did I call it 6? Now a 6 is when you have 2 similar groups on the same sides. So we have CH3 here, we have CH3 here, so this is a 6, okay, when you have 2 similar groups on the same side, that is a 6, alright. Then a trans is when you have 2 similar groups on opposite sides, like on different sides. So one is going up, the other one is going down. Alright. So let's use the same example again. We have CH3, C triple bond, CH3 plus hydrogen. Now we are using what now? Sodium in liquid ammonia. So when we use sodium in liquid ammonia, what are we going to get? A trans. So we now have this structure now, C double bond C. Then we have H here, we have CH3 here, and then we have H here, and then we have what? CH3 over here. Alright, so we have CH3 over there. So this is what we have. So remember, similar group on different sides. Similar group on different sides. So this was trans. So this will now be what? Trans boot 2 in. Alright? So when you use sodium in liquid ammonia, what do you get? A trans alkene. Then when you use Lindlar's cat, that's Lindlar's catalyst, which can be palladium with barium sulfate poisoned with sulfur, or we can have palladium with calcium carbonate, alright, poisoned with quinoline. So any of those ones, but I just used to use palladium and sulfur, right? Yeah. So don't forget 6, okay? So 6, alright. Then this one is what? Trans. So thank you very much for watching this video lesson. Please do well to watch, learn, go by again. Alright. Now in your examinations as a chemistry student offering organic chemistry in his or her first year in college and university, now you will see questions like this where your lecturer can just give you maybe something like this, put the catalyst and put a question mark here and ask you what will be the product, or sometimes they will give you the product and put a question mark, and they will ask you what is the catalyst being used. Take for example, now I do something like this. Watch this now. I do something like this. Let's say I decide to do this. Let me say arrow C, then C arrow. I do something like this, then plus H2. I put question mark here. Put a question mark. Alright. Then finally I got something like this. Then I ask you, what is the catalyst? This question mark is, so if I put a question mark like this and I'm asking you, what what's the mystery guy here? All right, so that's eventually a catalyst. So they are asking you, what is the catalyst that is used to heat this product? Now we have these two on the same side, arrow group. Arrow is an alkyl group. So we have two alkyl group on the same sides. All right, they are going downward. So that will tell you that what it is, what the Mendler's catalyst. So thank you very much for watching this video lesson, and I'll see you in the next video.